In section 2.2, we're going to introduce an important concept called the inverse of a matrix. We've talked about inverses before in math. One aspect is with a real number. So a real number A has an inverse A with the -1 symbol. And that means that if you take A and multiply it by its inverse, you get 1. So for instance, 7 inverse is 1/7 because 7 times 1/7, which is the same as 1/7 times 7, is 1. We've also seen the idea of inverses with functions. When you compose two functions together, like f of f inverse of x, you are left with just x. And that's a similar sort of idea here. We're going to have this now with matrices. So the definition, an n by n matrix A is said to be invertible if there is an n by n matrix C satisfying CA equals AC equals IN. We need both multiplications on the left and the right in order for the inverse to be true. And note that this is only true for square matrices. In order to have an inverse, it needs to be a square matrix. We talked about IN. IN is the identity matrix. That is 1s on the diagonal and 0 everywhere else. And then we call C the inverse of A if it exists. And then note that if A is an invertible matrix, then the inverse is a unique matrix. And we'll prove that fact very quickly here. So to prove it, we're going to assume that there are two different inverses, B and C. And we are going to show that B is equal to C, which means that there can only be one inverse. So if we start with B and we multiply B by I on the right, that doesn't change anything because multiplying by the inverse or by the identity I will not change anything. But then we can rewrite I as C inverse, or rather C times A, or A times C, coming from the idea of the inverse being AC equals IN. Then we can rearrange the multiplication with the associative property, and we get BA times C. But since B is also the inverse of A, we know that B times A is just I, so we get I times C, and we're left with just C. So again, we've taken any two inverses B and C, and we've now shown that they are equal. So the inverse is unique. We denote the inverse of A with A to the -1 power, just as we do with inverse functions. And we have that A times A inverse equals A inverse times A is equal to the identity matrix. Now it is very important that we note that not all square matrices are invertible. And a matrix which is not invertible is sometimes called a singular matrix, whereas an invertible matrix is sometimes called a non-singular matrix. So now let's look at how to find the inverse of a 2x2 invertible matrix. So we're going to let A be the matrix A, B, C, D. And if the condition that A times D minus B times C is not equal to 0, then A is invertible, and the inverse is equal to 1 over that expression AD minus BC times the matrix D negative B negative C A. We can get that matrix by switching the entries in the first diagonal, A and D, and then taking the negative of the entries in the second diagonal, BC. Note that if AD minus BC equals 0, then we get a 0 in the denominator of this fraction, which would cause issues, and in that case, A is not invertible. So for 2x2 invertible matrices, we have this nice formula that we can find A inverse very quickly, and we'll talk about how to find it for 3x3 matrices and more later on in this lecture. So now let's assume that A is any invertible matrix and we wish to solve the equation AX equals B. Then what we could do is if we take that equation and we multiply both sides on the left by A inverse, then we have A inverse times A is just equal to the identity matrix And then we are left with I times x equals A inverse B. But we note that I times x is just x, so x, the solution to our equation, is A inverse B. And then also, let's suppose that W is also a solution. We've seen that with AX equals B, sometimes there's more than one solution. Sometimes there are infinitely many solutions. So let's suppose there is another solution, W, to this equation. That means that A times W equals B. And we can play the same game. We can say that A inverse times AW equals A inverse B, which in the exact same work would show that W equals A inverse B, which means that W is the exact same thing as X. And as we showed with the uniqueness proof on the previous slide, that if W equals X, those are two solutions. This means that there's only one solution. X is the only solution. A inverse B is the only solution. And we proved the theorem that if A is an invertible n by n matrix, for each B in Rn, the equation AX equals B has a unique solution, X equals A inverse B. So for any B in Rn, the solution to the equation AX equals B, if A is invertible, is that solution, A inverse B. This is opposed to if we want to find that solution, we don't necessarily have to go through all of the row operations and determine if there's a unique solution or infinitely many solutions or no solutions. We are just given that this is the one and only solution to that system. So let's look at an example now. Let's use the inverse of A, where A is negative 7, 3, 5, negative 2, to solve this system of equations. And note that the matrix A is the coefficient matrix for this system of equations. So for this system, the matrix form of the linear system is the coefficient matrix A times X is equal to the right-hand side of the equation, the vector B. So we have AX equals B. And we said on the previous slide that the inverse is going to be in our solution. So let's find the inverse. The equation says that we need AD minus BC, and that to be non-zero. In this case, A times D is negative 2 times negative 7, and BC is negative 3, negative 5. This is going to be 14 minus 15, or negative 1. And since it's not 0, this inverse will exist. We have this 1 over 14 minus 15 in the expression here. And then the matrix negative 2 and negative 7 switch spots, and we take the negative of the 3 and the 5 and get negative 3, negative 5. Note that when we found AD minus BC, this should have been plus 3 and plus 5 as we're taking it from the original matrix. If we put all that together, we get negative 1 times that matrix, as this is negative 1, and we get 2, 3, 5, 7 as the inverse. So now that we've found the inverse, we basically have the solution to the system, because the solution is going to be A inverse times B. In this case, B is the vector 2, 1. So our solution will be 2 times 2 plus 3 times 1 is 7. And then 5 times 2 plus 7 times 1 is 17. And that is our one and only solution to the system. You can double check that by solving the system in a more familiar way by doing the row operations. It would take a longer time, but you would get the exact same thing out. So now let's think about some theorems with invertible matrices. First thing is, if you take the inverse of an inverse, you just get the matrix back. This is the same idea with any inverse kind of idea, with inverse functions as well. You're kind of undoing the same thing. That is that A is the inverse of A inverse. We had a similar idea with the transpose of a matrix in a previous section. Also similar to the transpose of a matrix, if you take AB inverse, you don't get A inverse B inverse, but you get the reverse B inverse A inverse. That's very similar to the transpose result that we had before. And thinking about the transpose, A transpose is an invertible matrix itself, and A transpose inverse is A inverse transpose. Those ideas can be switched. Let's look at part B and show why we have AB inverse is B inverse A inverse, why those matrices switch locations. So to do this, let's look at AB times B inverse A inverse. We're trying to show that this is equal to I. That if you take AB and you multiply by B inverse A inverse, you get I as a result, which means it's the inverse. If we take this and we just rearrange, so we take B times B inverse instead in the middle, then any matrix times its inverse is just the matrix I itself. Anything times I is just itself, so this will be A inverse, which is also I. In a very similar form, you could show that the reverse multiplication, which is needed, B inverse A inverse on the left, would also get you I. And then we can generalize part B of the previous theorem to more than one or more than two matrices. So just like we did with the transpose, we can say ABC inverse is equal to C inverse, B inverse, A inverse. You just reverse the order of the matrices and then put the inverse on them. So earlier we saw a formula for finding 2 by 2 invertible matrices. But the question is, how do we find the inverse of an invertible n by n matrix? And to do this, we're going to introduce a topic about elementary matrices. So an elementary matrix is one that is obtained by performing a single elementary row operation on the identity matrix. So in the first section of this course, we talked about elementary row operations. That is, we have 3 of them. We can take a row and we can swap it with another row. We can take a row and we can multiply it by some scalar. Or we can do the one that we do more than anything, which is we take a scalar times one row, add it to another, and that becomes our new row. Our 3 row operations that we use to row reduce a matrix. So if we take any of those operations and perform one of them on the identity matrix, that's what we're going to call an elementary matrix. So we have 3 matrices here that look close to the identity matrix but are different. We're going to show that each of these are elementary matrices corresponding to a single elementary row operation. So the first one, if we take the identity matrix and we do the row operation 2 times row 2 is our new row 2, we get the matrix E1, which has 0, 2, 0 as that second row. The second matrix is we have swapped row 2 and row 3. And the third matrix, we have taken 3 times row 1 plus row 3, and that became our new row 3. Note that nothing else changes except for that bottom left corner, this 3, because everything else has zeros with it. So elementary matrices are very close to the identity matrix. In fact, they differ just by one elementary row operation. And these elementary matrices are going to be our building blocks to find the inverse of a matrix. So given those same 3 elementary matrices and a generic matrix A, B, C, D, E, F, G, H, I, we're going to describe how the following products can be obtained by elementary row operations on A. And we will show that they're going to coincide with the row operations that we just found. So if I take E1 times A on the left, E1 multiplied by A on the left, and we go through all of those multiplications. So again, what we're doing here is for the first entry, we take 100 plus ADG. We'll get 1 times A plus 0 times G plus 0 times G equals A. We have to do this 9 different times. Another one right here. If we take the second row in the third column, that would give us 2F. And again, we do that 9 times when we get the matrix ABC, 2D, 2E, 2F, GHI, which corresponds to, if I go A and I row reduce to get E1A, what I'm doing is 2 row 2 into row 2, which is the same row operation that we found to get from I to E1. Let's do the same thing for E2. We'll see that it's going to be the same idea here, that if we go from A into E2A, all we're doing is we are taking the second row and we are switching it with the third row. And again, if you go through all of these calculations, all 9 of the calculations, you take a row times a column, you get the entry out, you would get the matrix associated with that elementary matrix, that elementary row operation. And same for the third one, E3 times A, you would get 3 row 1 plus row 3 into row 3. The same operations that we described on the previous page. So what I want you to take a look at is, again, that this row operation is the same row operation that we take from to get to A to E1A is the same operation we get from I to E1. And this elementary matrix encodes the information about that row operation in some way, and again will be the building blocks of our inverse. So if an elementary row operation is performed on an m by n matrix A, doesn't have to be necessarily a square matrix, could be a rectangular matrix. The resulting matrix can be written as E times A. We've seen that on the previous page. And E is an m by m matrix created by performing some row operation on the identity matrix. And the elementary matrices themselves are invertible because row operations are reversible. Let's think about those real quick. How do we do the reverse? That is the idea of the inverse. Of elementary row operations. Well, if we have row switching, if we switch row I and row J, the inverse of that is just switching them back. If we take a scalar and multiply it by a row, what we could do is we could multiply by the inverse of that scalar, 1 over alpha, and that gets us back to where we were before. And if I take if I take a constant times row I and add it to row J, and that becomes my new row J, we get another reverse operation. And since this corresponds to the example right here, let's try to find out what that operation will be. So we're trying to find some operation here that will get us to the identity matrix. So we're trying to get from E3 to the identity matrix. In that case, what we need to do is get rid of that 3 in the bottom left corner. That'll be negative 3 row 1 plus row 3 into row 3. And that'll get you the identity matrix back, and the corresponding inverse here will be corresponding to that row operation, which will be the same thing except a negative 3 in that bottom left corner. Or in general, we have negative alpha row I plus row j would be the new row j as the reverse elementary row operation of that third kind of elementary row operation. So again, the key here is because we can reverse the elementary row operations, we can take the inverse of these elementary matrices as well. So let's do an example here. We have this matrix A, 1, 0, 0, negative 3 halves, 0, 1 half, 0, 1, 0, and we are going to try to reduce A into row echelon form. And note that there are a number of ways that we could do this, a couple different steps that we could do. We're going to look at 3 different row operations corresponding to our 3 elementary elementary matrices that we found in the previous examples. So the first thing we might want to do is get rid of the fraction in this second row, the negative 3 halves and the 1 half. And the way we could do this is we could multiply that row by 2, which is the same thing as multiplying by that matrix E1. Again, the row operation here is 2 row 2 into row 2. And the corresponding multiplication will be the same thing as if I did the row operation on A. And we would get negative 3, 0, 1 in that second row. Then if I take that new matrix E1A and I multiply it by a new elementary matrix, that is doing another row operation on the matrix. And in this case, we're going to do row 2 switch with row 3. And this is to get a pivot in that second column, second row position. We want to get a pivot in that middle, and we could do that by switching the second and third row. Again, if we multiply by that elementary matrix to that matrix A, or to that new matrix E1A, then we get the corresponding matrix that we would get if we row reduced, switching the second and third row. And then we have our new matrix E2, E1A. We're going to multiply that by a third elementary matrix. In this case, this is the one that takes 3 row 1 plus row 3 into row 3. And again, we would get the identity matrix out. Again, because we saw that this matrix here was E3 inverse on the previous page, so E3 would be the matrix I would need to get to the inverse itself. So what we have here is E3, E2, E1A is equal to the identity matrix I3. And this shows us that we can now find the inverse, which we're going to show on the next page. If we take that equation and we multiply on the right by A inverse on both sides, we get that E3, E2, E1 times the identity matrix, that's from the A inverse, equals A inverse, or simplified, A inverse is equal to those elementary matrices multiplied together, E3, E2, E1, noting that the order of that multiplication is important. So bringing it all together, we have the elementary row operations that row reduce A to the identity matrix. This is the idea that we brought in the first 2 sections of this course. Those are the same elementary row operations that transform the identity matrix into A inverse. And we get this theorem that an n by n matrix A is invertible if and only if A is row equivalent to the identity matrix. And in this case, any sequence, there's more than one way to get to the identity, any sequence of elementary row operations that reduce A to In will also transform In into A inverse. So again, this is saying if A is invertible, if it does have an inverse, then if we take the matrix A and we perform a bunch of row operations on it, we would end up with the identity matrix at the end. That is a matrix in row reduced echelon form. It has 1s on the diagonal, 0s above and below those 1s. All the rows and columns have exactly 1 pivot. That corresponds to 1 unique solution to the system of equations if that's what we are talking about to row reduce. This idea that if we row reduce A to IN is the same as row reducing IN to A inverse is going to be our algorithm for finding the inverse of A. We'll see that on the next page here. That if I place A and I side by side in an augmented matrix, so this time the bar, the augmentation, is not necessarily corresponding to an equal sign, but we're just trying to break up this long rectangular matrix into two square matrices, A and I. And we perform row operations on the matrix, which will produce identical operations on A and I. By the previous theorem, AI will row reduce to IA inverse because A will row reduce to I, and I will row reduce to A inverse. If you go back to the previous page, that's what we were saying in this statement right here, that the same row operations that reduce A to I inverse are the same that reduce I to A inverse. Or, if A is not invertible, we would find a different reduced echelon form. We would reduce AI to something that is not I times some other matrix. Something that's in row reduced echelon form, but not I. So maybe you would row reduce it to something like this. We have a row of zeros on the bottom, and that would just tell you that A is not invertible, that you cannot row reduce to the identity matrix and therefore not invertible. So let's see an example of this. Let's find the inverse of A, 2, 0, 0, negative 3, 0, 1, 0, 1, 0, if it exists. We're going to know if it exists if I can row reduce to the identity matrix, and if not, it does not exist. So A augmented with I, we have a 3 by 6 matrix with a bar in the middle, the matrix A on the left, the matrix I on the right. And if I row reduce, I would get to the point that I get the identity matrix on the left and the matrix 1 half 0 0 0 0 1 3 half 1 0 on the right, which tells me that the right hand side is my A inverse. Note that we are doing row operations to get from the two matrices together. Those row operations might be 1 half row 1 into row 1, then a 3 row 1 plus row 2 into row 2, and then I believe a row 2 switching with row 3 would be the row operations we need to get to that last spot. Again, this is an algorithm for finding the inverse of a matrix, which will be very useful in a lot of different ways. Notably, one way is to find solutions to equations, but we're also going to use the inverse a lot more in this course. So it's important that the order of multiplication is important. We showed that AB is not the same thing as BA in general, and because of that, we have to be very careful with the multiplication in ways that we do not have to care about at all with real numbers. So let's look at this example. We have A, B, C, and D are invertible n by n matrices. That means that A inverse, B inverse, C inverse, and D inverse exist. And we have this expression A equals B D minus I times C. We're going to solve for D in terms of A, B, and C. This is some practice dealing with the algebra associated with the inverses of matrices. So if I want to solve for D, if I want to get D by itself on one side of the equation, I need to move everything with D to the other side of the equation, and I need to do that by using the inverses. We cannot divide by matrices. We have no way to do that, but we can multiply by inverses to get rid of matrices on either side. So for instance, if I want to get rid of the b attached to the d minus I can multiply on the left by b inverse on both sides, noting that b inverse b will give me the identity matrix. And similarly, to get rid of c, I can multiply by c inverse on the right. And again, c times c inverse would give me the identity matrix. So b inverse would give me I, and c inverse would give me I. Anything times I is just itself, so on the right-hand side we're left with just d minus I times b inverse a, c inverse. Then, to get rid of the identity matrix, I can add a copy of the identity matrix to both sides. This cancels out the negative in plus in, and I am left with d is equal to b inverse a, c inverse plus I. So one purpose of the identity matrix we showed in this lecture is that we can use it to find solutions to systems of equations, that being x is equal to a inverse b for any b. That's a nice thing that we can show for invertible coefficient matrices. And then also, invertible matrices are going to be useful for doing algebra on equations that deal with matrices. Because we cannot divide by matrices, we have to multiply by the inverse of matrices instead. And if they did not have inverses, then it would be very difficult to solve an equation or impossible to solve an equation like this.